So it's a very great pleasure for welcoming everybody to our March edition of Lagoon. And we have the pleasure to have today as a speaker Emanuele Pavia from CISA, Trieste, and he's going to talk about sheaves of categories over topological and coaffine stacks. Emanuele.
Thank you very much for the invitation and for the introduction. So today I want to present you some results that I, Nicolò, and James are working on our ongoing project that hopefully will be soon finished on local systems of categories and categorical sheaves. So the plan of the talk will be the following. First, I will introduce a bit of the terminology and the notations for talking about local systems over topological spaces, at least in the homotopy-coherent and derived world, in order to fix a bit of the notation and see how the classical picture generalizes to the homotopy world, and talk about the monodromy equivalence that will be like one of the basic tools that we will generalize in the categorical setting. Then we will see the main characters of the talk that are Betti stacks and coaffine stacks associated to topological spaces, and quasi-coherent sheaves over them in order to see how they interact. Then the core of the talk will be the third part that will deal with categorified quasi-coherent sheaves on both coaffine and Betti stacks. And finally, if time allows it, I will talk a bit also on the n-categorical picture that we are still developing right now. So first, we will assume that we are working on a base field K of characteristic 0. And all notions, in order to trim a bit our notations, are already derived. So if I talk about category, I mean infinity category, or when I'm talking about some presentable and k-linear category, I just mean DG categories. Limits and colimits are to be meant in the homotopy sense, and k-modules mean actually chain complexes of k-modules in the derived category, etc., etc., etc. And I use the homological indexing conventions. So we can start. Let X be a sufficiently nice topological space for our setting. Since we are working up to homotopy, a CW complex will suffice. So you can really think the best topological space you can have. So you can define a category of sheaves over X also in the homotopy world, just like in the classical setting. So you have the category of opens on open subsets of X with the topology given by the actual topology of X, and you just take the sheaves with values in the category S of spaces up to homotopy. And this is a topos and admits an hypercompletion that morally just takes the sheaves whose equivalences can be detected at the level of the stalks. So this hypercompletion is actually a full subcategory, is a localization of the category of sheaves over X. And the inclusion admits a left adjoint that is called hypercompletion functor. So actually these hypercomplete sheaves do not arise in the classical setting. It's something that appear only when one works with infinity categories. But actually hypercomplete sheaves are the best options that we have in the homotopy setting in the following sense. So we say that F is an hypersheaf if it actually belongs to the hypercompletion of the category of sheaves over X. And so, of course, just like in a classical setting, you can pull back and push forward morphisms along morphisms of topological spaces. So, for example, if you take a map from of topological spaces, then you can push forward and pull back and get another sheaf on the other space. But for hypersheaves, you have actually to pull back and push forward and then hypercomplete, because in general it will be, you will get only a sheaf and not an hypercomplete sheaf. So in particular, we apply this machinery to the terminal morphism from X to the point, and we say that F sheaf is hyperconstant if it belongs to the essential image of the functor that is described as follows. So you have the category of sheaves over the point, which is just the category of spaces. You pull back to the category of sheaves over X, and then hypercompletes it. So if something belongs to the essential image of that, we say that is hyperconstant. And we say that it is locally hyperconstant if there exists a covering of the topological space such that the restriction of the sheaf to each element of this covering is hyperconstant. It's really just the same as constant and locally constant sheaves up to this hypercompletion operation. That actually is quite important, because if you take constant and locally constant sheaves and you say that they are hypercomplete, in general, you do not get those hypercomplete and locally hypercomplete sheaves. You really get some full subcategory of that, except for certain topological spaces which are particularly nice. So you could say which is the best option between the two, and this result that is quite available in the literature, it is proved in many places, says that locally hyperconstant hypersheaves are the correct notion of local systems over topological spaces in the homotopy theory. Because if you take X, the topological space, and you take its fundamental groupoid, that sometimes is called Sing X, if that notation is more familiar with you, then there exists an equivalence of categories between locally hyperconstant hypersheaves on X and functors from the fundamental groupoid to spaces. So really, the homotopy theory of the topological space is encoded in locally hyperconstant hypersheaves. So for this reason, we set this notation. For any category with enough colimits, we write that the category of local systems over the space X with coefficients in C is just this category. So now we talk about the monodromy equivalence that actually generalizes a well-known result in local system theory. So take again, see your favorite complete category, and then the category of spaces acts via colimits on C. In this way, you simply take a space and an object of C, and then their tensor product is just the colimit of shape X of the constant diagram with values in C. So in particular, if X is an object that is like a monoid or a group object in topological spaces, you can say that an object of C is acted on by that topological space. And this proposition that it is called monodromy equivalence says that for X, a connected topological space, you take its base loop space that is just like the space of loops over X with a certain base point, with the compact open topology. If X is sufficiently nice, then that will be a topological space, a well-defined topological space. Then the category of local systems is just the category of objects with an action of the base loop space. So how this generalizes the classical picture? If you take C, the derived category of K modules, then you can take both, on both sides you have a T structure. Okay, so on both sides you have a T structure. On the left-hand side, you recover the classical category of local systems of coefficients with values in K modules. On the right-hand side, you get the category of K modules with an action of the H0 of the chains of the base loop space. But this H0 is just the group algebra over the fundamental group of X. So we are just recovering the fact that, or better, generalizing the fact that local systems over a topological space are more or less objects that are a representation of the fundamental of X. So this was just like the main technical framework. So we have actually a way to encode the topological spaces in the setting of derived algebraic geometry. Because in derived algebraic geometry, we deal with derived stacks that are essentially some sheaves for the Tal topology on the category of affine schemes with values in the homotopy category of spaces. So the category of affine schemes, I should remark it quite well, is just the opposite of the category of differential graded commutative algebras, which are connective. That is, have homology concentrated only in non-negative degrees, or if you work in the cohomological setting, only in negative degrees. So in particular, you have this category of stacks for the Tal topology over K. And you can, of course, since the category of affine schemes has a natural functor to the point category, you have this geometric morphism of toposes, the one on the bottom of the picture. And the Betti stack of a topological space is just the image of the fundamental groupoid of X under this geometric morphism. So it's just this sheavification of the constant functor with values X. This is quite a well-known construction in algebraic geometry and number theory, because, for example, objects with an action of the circle are just stacks with an action of the Betti stack of the circle. So since they are stacks, we can consider both a commutative algebra of global sections and a DG category, stable K-linear and symmetric monoidal category of quasi-coherent sheaves over the Betti stack of X. And even if the Betti stack is quite difficult to grasp, we really understand well these two objects, because the algebra of global sections is just the algebra of the k-valued cochains on the topological space. And for any affine scheme, there is a symmetric monoidal equivalence between the quasi-coherent sheaves over the Betti stack times the spectrum of R and the local systems of X with coefficients in R modules. So in particular, if you take spec K, this just says that the quasi-coherent sheaves on the Betti stack are local systems of K modules over X. So in some way, there is a natural way to encode topological spaces and their homotopy theory inside the world of derived algebraic geometry, and to work with cohomological properties of these topological spaces in the derived setting. And the fact is that, as I said before, Betti stacks are quite pathological, because as pre-stacks, they are constant, but their sheavification is quite difficult to understand. So Toen introduced many years ago the notion of affinization of homotopy types that allows to consider stacks which are not affine, actually, are not affine schemes, but still they are a good approximation and by stacks that we can actually deal with and do computations with, because they are quite similar to share many similar properties with affine schemes. So this is the definition by Toen, and then it was rewritten in a more modern language by Lurie. We say that a connective algebra, so an algebra that is A, is just an algebra, a commutative differential graded algebra, whose homology is concentrated in homological negative degrees. So it's in some sense like the other side with of the affine schemes. Affine schemes are concentrated in homological non-negative degrees, and these are going on the other side. And the zeroth homology is just isomorphic to K. And a coaffine stack is any stack that is co-represented by a connective algebra like this. So it's a stack that is equivalent to a functor like this. Let me remark that this is actually a stack, not a pre-stack. You do not have to sheafify anything. This is already a stack that satisfies a Tal descent. So just for notation, if X is coaffine, so is equivalent to a functor like this, we write that X is the cospectrum of A. So, okay. So there are many similar properties that link coaffine stacks and affine schemes, because, for example, if you have a stack, to give a map from that stack to a coaffine stack cSpec A is the same as giving a map of commutative algebras from A to the global sections, just like for affine schemes. And just like for the case of affine schemes, the cospectrum functor produces a fully faithful embedding of the category of co-connective algebras inside all stacks. And so every coaffine stack is determined actually by its values on discrete, that is classical, not derived commutative algebras. But there is a difference between coaffine stacks and affine schemes, because just like in the case of affine schemes, and actually in the case of all vol stacks, you can take the category of quasi-coherent sheaves over the co-spectrum of A. That by definition is just is defined as a limit of the categories of R modules, where the limit is computed with respect of to all affine schemes that map to your coaffine stack. And if you take this construction over an affine scheme, then you get actually the category of A modules. But for the coaffine stacks, this does not hold. But we have still like a very, very close relationship between the two. So consider a coaffine stack. Take so since the H0 is isomorphic to K, there exists a natural pointing eta from spec K to X that corresponds to the map to the augmentation, the natural augmentation from A to K. So you can consider the category of quasi-coherent sheaves over X, and this admits a T structure that is both left and right complete, and an object is co-connective or connective if and only if you pull back it over spec K, then it is a complex of K modules, and you just say that it is connective or co-connective for the standard T structure on the derived category of K modules. On the other hand, the category of A modules has a bit trickier T structure because it is right complete, but not left complete. An object is co-connective precisely if you pull back it over K modules, and then it is co-connective in the classical sense. But connective objects are detected in a different way. Choose your favorite map of commutative algebras from A to R, where R is connective. Then you say that A module is connective if it is its base change over R. And then the naturally defined functor that we have like this, because since Q co X is defined as a limit of all the modules of the category of R modules with spec R mapping to X, there is a functor like that. And this functor exhibits the T structure on the quasi-coherent sheaves over X as the left completion of the T structure on mod A. So this in particular tells that if you consider only bounded objects, then these categories are actually the same. What goes wrong for objects that are unbounded in both directions. So in order to sum it up, for given a topological space, we have a natural map like this. We have two different stacks, the Betti stack and the coaffine stack, represented by the cochains. And this map is induced by the identity map because, as I told you, the global sections are the same. And so this will be like the main picture that we are dealing with in the following. So for any pointy stack like this, we denote by this QCO small the full subcategory of quasi-coherent sheaves over X spanned by those sheaves whose pullback on mod K is a perfect object. So is quasi-isomorphic to a bounded chain complex, which is projective and finite in each degree. And then we have this following proposition that is like more or less in Luri's work, but there is a part that is not available in the literature. If you take the X, a topological space which has the homotopy type of a connected CW complex, such that this CW complex is obtained by attaching only a finite number of cells in each dimension, we have this commutative diagram of stable categories. So here we have the modules over the algebra of cochains. Here we have the quasi-coherent sheaves of the coaffine stack represented by the cochains. Here we have the quasi-coherent sheaves over the Betti stack. And here this weird object that is just the incompletion of the category of small quasi-coherent Betti stacks. This is a bit fancy, but it is actually a generalization of a well-known result in Koszul duality. That is, if you take your space which is connected and finite, then this in the Q-cosmol, is just the category of incoherent sheaves over the algebra over the chain algebra of the base loop space of the space. And on the other side, you have the modules over the cochains algebra. And the Koszul duality framework tells you that under these assumptions, the Koszul duality functor produces an equivalence between modules over the cochains and these incoherent sheaves over the base loop space. And the other part just tells you that the modules over the base loop space correspond to the quasi-coherent sheaves on the coaffine stack represented by the cochains algebra. So if there are any questions, or otherwise I will proceed to the core of the talk. So first, in order to talk about local systems of categories and sheaves of categories, we need to fix a bit some notations and some reminders on presentable categories, which will be like our favorite coefficients. So a presentable category in general is just a category which admits all colimits, and even if it is large, is still generated by a small set of compact objects. So every object is just a filtered colimit of a small set of compact generators. So for example, all categories of modules are presentable because every object is just a filter colimit of perfect objects. So the main facts that we will use in the following are these. There is a two category of presentable categories, which as objects, just presentable categories. And as morphisms, it has a full category of colimit preserving functors, which in the setting of presentable categories is just the same of functors which are left adjoint. And these two categories admits a symmetric monoidal structure, and the symmetric monoidal structure has a particular property, that is a commutative algebra inside the PRL is simply a presentable category which is symmetric monoidal, and such that the tensor product commutes with colimits separately in each variable. Again, for example, if you take the derived category of R modules with the derived tensor product, then this is a presentably symmetric monoidal category. So it's just a commutative algebra in PRL. So in particular, since the category of K modules is a commutative algebra object, we can just generalize the algebra of commutative algebra and modules to the categorical setting, and we can say that a presentable category is K-linear if it is a module for the presentably monoidal category mod K equipped with the derived tensor product. And notice that this is equivalent to C being enriched over mod K. That is, every mapping space is actually a chain complex of K modules. So this is really the, if you want, this is just the a presentable category is K-linear if it's a pre-triangulated DG category, which is K-linear. And so we will deal mainly with the category of K-linear presentable categories. So in one affineness work by Gaitsgory, Gaitsgory proposes a following categorification of the concepts of quasi-coherent sheaves and affineness. So first, you consider any pre-stack. Not it is not mandatory to consider a topological or coaffine stack, and then you define by descent the two categories of sheaves of categories over X. That is just the limit inside PRL of these presentable categories. That is, you can imagine a sheaf of categories over a stack as a rule that to any affine scheme that maps over X, you get a R-linear presentable category. such that everything glues together along morphisms. So it's really the categorification of the concepts of sheaves of modules. And to any sheaf of categories, just like in the classical setting, you can associate a global section category, which is linear over the category of quasi-coherent sheaves over X in the following way. You take, you have the local sections over any affine scheme that maps over X. You push it forward along the morphism iota R, and you get QCoX linear category. And then you just take the limit over all these objects. Notice that if you decategorify this picture, this is just the way you construct the global sections of quasi-coherent sheaves in the derived setting. On the converse, if you start with a QCoX linear category, you can obtain a sheaf of categories just by sheafifying this rule. To any affine scheme over X, you just associate the category C tensor product over QCoX of mod R. Notice that the tensor product is to be understood in the following way. PRL is a symmetric monoidal, as I told you. QCoX is a presentably symmetric monoidal category, so you can consider a relative tensor product over that, and you get this operation, just like in the setting of relative tensor products of commutative algebras. So with these notations, we can define what one affine stack is, and see, these functors are always adjoint. Log X is the left, and the enhanced global sections are the right adjoint. But a stack is one affine precisely if this adjunction is an adjoint equivalence. So if actually any sheaf of categories over X is determined by what happens on the global sections with their QCoX linear action, and then everything is obtained by base change. And notice that the idea is to categorify this picture. We can say that a stack is weakly zero affine if the category of quasi-coherent sheaves over X are just modules over the global sections of the structure sheaf. In the categorified setting, we have a categorical structure sheaf that is this calligraphic QCo over X that is defined by the rule that to any affine scheme over X, you map it to mod R. And so you can interpret one affineness as a categorification of zero affineness, because this just tells you that sheaves of categories over X are just modules over the global sections of these categorical structure sheaves. And some examples in order to see what we are talking about. So affine schemes are naturally one affine because actually everything is determined on what happens on spec R because it's cofinal. So that limit, that huge limit is simply a limit over the one object spec R. But objects that are not affine can become one affine. For example, if you take a classical affine group scheme of finite type and you take the classic affine stack, then that is one affine. And formal completions of quasi-compact and quasi-separated algebraic spaces along closed subsets with a quasi-compact complement are again one affine. Some things are not one affine, of course. So for example, if you take in schemes in general fail to be one affine, even really basic in the schemes. So for example, the co-limit over all n of the n affine n space and dimensional space is not one affine. Okay, so now let's step back to the topological picture. Start with X topological space, and it is true that the two categories of sheaves of categories over the Betti stack is naturally equivalent to the category of categorical local systems. That is just functors from the fundamental groupoid of X to the category of K-linear presentable categories. And this is very simple to see, because this is true because both sides, both Sheaves cut and log-sys cut, sends co-limits of pre-stacks to limits of presentable categories. So both sides are equivalent to this limit. You present X as a co-limit of the contractible cells that constitute it, and then you get this limit. Okay. This is a categorified monodromy equivalence that will be used in the following. If X is a pointed, now simply connected topological space, there exists an equivalence of two categories between these. So we can really describe sheaves of categories over X as presentable categories which are linear over the chains over the base loops, over the twofold base loop space over X, if X is simply connected. And this is actually quite easy to see, because of course, if C is co-complete, the local systems over X are simply equivalent to the representations of the base loop space. In particular, since PRL is co-complete, this applies also in this setting. So one proves that for any presentably monoidal category C, there exists an equivalence of two categories between representations of the base loop space inside C-linear presentable categories and modules over the local systems with the values in C of the base loop space. So this is just like when you say that you want to construct a group representations in commutative algebras. This is just the same as a module over the group algebra. This is just a categorified picture. So if X is simply connected and the base loop space is connected, one proves that the equivalence between local systems and modules over the base loop space is monoidal. And in particular, the deconvolution on one side becomes the relative tensor product over the E2 algebra omega square X. So if you concatenate everything all together, you get actually the equivalence that we had here. And this recovers actually also a result by Telemann in a work of 2014, that a topological group action of a connected topological group G on a DG category, on a K-linear DG category C, is equivalent to the datum of an E2 algebra morphism between the chains of the base loop space of G and the Koszul cohomology of the category that is defined as just the X algebra of the identity functor. And the idea of the proof is the following. Every connected topological group is the base loop space of some space. So you can apply the machinery of the previous theorem and write a G action on C as just a left L mod C omega G module structure on C. But now, just like in the classical setting in which to have a module, an A module structure is the same as a morphisms of algebra between A and the endomorphism algebra of the module, you can say that L mod C omega G module structure is the same as a monodal functor between these two categories. And this, by abstract nonsense due to Lurie, is the same as the E2 algebra morphism between the base loop space of the group G and the Koszul cohomology of C. This is just because there exists an adjunction that tells you that L mod is the left adjoint of taking the X algebra of the identity functor. So this allows to grasp a bit better what are sheaves of categories over Betti stacks. And so we can ask when a Betti stack is one affine. That is, when K-linear categorical local systems coincide with modules over the category of K-linear local systems. And first, we can just say that every module over local systems of X become, or better, the category of local system modules in PRL are fully faithfully embedded inside the local systems of categories. In general, this is not true. Like they are adjoints, but there is no reason why one of the two functors should be fully faithful in principle. So it is quite remarkable that for any topological space, this functor is always fully faithful. And the proof is actually an application of the Barbach-Luris monadicity theorem. You just see that there is a commutative diagram of monads, and the functor is an equivalence precisely if categorical local systems are monadic over PRL. So this is one of our first results on affineness of Betti stacks. If you start with a one truncated topological space, then its Betti stack is one affine. And the idea of the proof is the following. If X is one truncated, then its base loop space is equivalent, a better up to homotopy, to a discrete group G. And by a work of Gaitsgory, if G is a group pre-stack for which lock G is fully faithful, then its classifying stack is one affine if and only if the global sections functor at the decategorified level over G are monadic. So you apply this machinery to the Betti stack of the base loop space. That is just the base loop space of the Betti stack of X. You obtain that taking the global section is just a product. So local systems over discrete group are just a collection of modules indexed by the elements of the group. And taking global section is just taking the product. And this is a monadic operation. So in particular, it follows that the Betti stack of the circle is one affine, but this actually was already known in the literature. It was never spelled out explicitly, but if you glue some results here and there, it becomes known. Betti stacks of this joint union of Eilenberg-MacLane spaces K pi 1 are one affine. So group topological spaces that have homotopy only degree 1 are one affine. And the Betti stacks of Sn for n greater or equal than 2 of Eilenberg-MacLane spaces of groups concentrated in degree 2 for pi and abelian group and CP infinity are not one affine. These are not just conjectures, but really you can put your hands in the dirt and do computations and see that that functor, the global sections functor from the base loop space will never be monadic. So this is actually something we are working on. I think there are some issues to still understand, but does every one affine Betti stack come from a one truncated topological space? So can we reverse the implication of the previous theorem? And this is still open, like we are still working on that. So we have seen what happens between in the setting of Betti stacks, but we can also see what happens, what is the relationship within sheaves of categories over the Betti stack and sheaves of categories over the coaffine stack of a topological space. So let X be appointed to connected topological space. To connected means that the homotopy groups 0 and 1 and 2 are all trivial, and all the homotopy information is concentrated in degree 3 and above, such that the algebra of K-chains over the base loop space has finite K homology in each degree. This is a technical condition to make the Koszul duality work. Then the pullback over the affinization morphism. The affinization morphism was the one between the Betti stack and the coaffine stack that was introduced some slides ago. This functor restricts to an equivalence between sheaves of categories who have local sections over this point spec K, which are dualizable as objects in K-linear presentable categories. Dualizable objects are really understood. They are like compactly generated DG categories or retracts of compactly generated DG categories. So you can really see when a sheaf of category meets this condition. And so since now under these assumptions on X, we still have that the local systems, categorical local systems over X are modules, categorified modules over the twofold base loop space, we can see that this is in some sense a categorification of the classical Koszul duality between modules, between these E2 Koszul dual algebras. It is known that under these assumptions, the algebra of cochains on X and the algebra of chains of the double base loop space are E2 Koszul dual, but there was not known it was not known if there was like a correspondence between modules. And this categorified picture really provides a generalization of the Koszul duality between modules of the E1 Koszul duality case. And the proof, again, is just an application of actually of a consequence of the main consequence of the Barbach-Luris monadicity theorem to this diagram. And where these functors is just the pullback along the pointing over X. Everything works finely, but there is an issue. In order to apply the Barbach-Luris theorem, you need this diagram to commute even if you replace eta star and eta Betti star with the left adjoint. But this is not true. The right adjoint, sorry. Because if you take the right adjoint, in general, this diagram does not commute anymore, so you cannot apply the Barbach-Luris theorem. And in order, why the dualizability enters the picture? So you really need the first. This is just what why we need the finiteness assumptions on X and its base loop space, because then you can apply the classical Koszul duality picture and write this thing. And then on the second side, in general, this limit is not equivalent to the tensor product of C with the quasi-coherent sheaf category of quasi-coherent sheaves over this coaffine stack. But if the category C is dualizable, then it commutes, the tensor product with it commutes with limits, and you can bring that limit inside, and so you have an equivalence. And so in particular, if you take the right adjoint to this in this diagram, this diagram now commutes. So this is how we use the dualizability for our statement. And it is really a strong result. Like you cannot hope to better this picture without assuming dualizability or without making further assumptions on X in general. Because, for example, if you take CP infinity or the classifying space of CP infinity, then their Betti stacks are not one affine, but the associated coaffine stacks are one affine because they are proved to be one affine in Gaitsgory's work. So we can ask ourselves if there is if that functor can be promoted to an equivalence on the whole categories if X is sufficiently connected or finite. So if it has some assumptions more on their on its topological aspects, but I'm quite I'm not so sure about that actually. So actually we can generalize this picture also the level of n categories. And so what is an n category? An n category should mean a category with the objects, and instead of a space of morphisms, we now have a n-1 category of morphisms. So a 2 category is a category with objects and a whole category of morphisms between objects. A 3 category is a category with objects and a 2 category of morphisms, etc., etc., etc. For this reason, in general, in literature, we write the category of n categories like this. And like this, they are just categories, but they can be promoted to n categories, n+1 categories via by turning these their enrichment into another by changing the spaces essentially of their mapping objects. So we have also in the setting of n categories a notion of presentable n categories. that is due to work by Stefanich. And presentable n categories are defined as follows. So take the category of complete n categories. We assume we start from n n equal 2, because we already know what is the 2 category of presentable categories, and then we just go by induction. And so you just take the category of presentable n-1 categories, and take the modules over that inside the category of complete n categories, and then, take the K0 compact objects, where the K0 is just the smallest large cardinal for our theory. Recall that we have had fixed 2 universes, so K0 is the first cardinal, which makes something V small but not U small, essentially. And so how they interact with the ordinary theory of presentable categories. For n equal 1, you obtain just the classical category of presentable categories. For every n greater or equal than 2, then these can be promoted to actually an n+1 category, which admits all colimits. It is not known if it admits all limits, but at least it admits a sufficient amount of limits that allow to do theory and algebra inside that. And they are equipped with a symmetric monoidal structure, which is compatible with colimits in each variable. Moreover, the unit in the category of presentable n categories is PRL infinity n-1. And you can also take k-linear coefficients by considering, by starting like this. So you say that k-linear presentable categories is just modules over k mod in PRL, and then iterating the process as before. So you take K0 compact objects inside the category of n of complete n categories for the category of k-linear presentable n-1 categories. So everything is defined inductively. The reason why we are always taking these compact objects is because otherwise we would always explode in another new universe, which is larger than the first. But taking the K0 really resets the theory to the V universe that we had started with. And you can also, just like there is the yoga that En monoids are just En monoidal categories with 1 object. And this is just like a description that Stefanich does of this picture in his work. So start with a En+1 algebra and n greater or equal than 0. We now produce a n+1 category of iterated left-hand modules as follows. So for n equals 0, you're starting with a E1 algebra, so an associative algebra, and so you just take the category of left modules over A. For n greater or equal than 1, then the category of n-1 fold modules is a presentably monoidal n category. So in particular, it is an algebra, and you can take modules over that algebra. And so you define L mod n as modules for this algebra inside PRL infinity n-1, and take this category. And for n greater or equal than 1, if you start with A equal k, you are just taking the category of presentable k-linear infinity n categories. So really, there is a connection between presentable n categories and n-fold A modules. So now we can deal with the categorical local systems of n categories that are defined just like in we defined them before. So as n functors from the fundamental groupoid, which is seen as an n category in a trivial way, to the category of presentable n categories. And the monodromy equivalence can be furtherly categorified as follows. So n categorical local systems over X, where X is n connected, so every homotopy group up to level n is killed, is equivalent to the category of modules inside the PRL n, over the n-fold modules over the n+1 fold base loop space. This is like a bit tricky, but it's just you just iterate the equivalence every time. You have you can always the looping you can always take the loops once again, because X is sufficiently connected, and you just get an iterated category of modules on the right hand side. And the strategy of the proof is works because works just like in the case of the two categorical case, because the definition of presentable n categories by Stefanich really retains all the key features of the original presentable categories that we used in the first place. So you just prove that using this fact, you can prove that there is an equivalence on the underlying one categories, and then see that this equivalence actually matches with the enrichment over PRL infinity n. So it is really simple. It is more difficult to provide the theoretical framework where to work with rather than providing the proof of this fact. And Stefanich also provides a generalization of shapes of categories and n affineness as follows. So you can take the n+1 category of shapes of n categories, just like before. You take the limit over all affine schemes mapping to your pre-stack, and you take the limit of the category of n-fold modules over R. Since R is commutative, you can take every iterated module as many iterated modules as you want. And this limit is computed in the category of n+1 presentable categories. And X is n affine if the global section factor that is defined naturally is monadic. And for n equal 1, this is just the notion of one affineness of Gaitsgory. You can prove it that they are the same. And this follows because the monadicity, at least in this case, can be checked at the level of the underlying one category. So really, even if you are dealing with a huge amount of structures, you can forget everything and just consider an ordinary one category and check everything at that level. So now I conclude with these last results that we obtained for Betti stacks. So if for any space X and for any n greater or equal than 2, then the Betti stack of X is n affine precisely if the base loop space has a Betti stack which is n-1 affine. So in particular, if you concatenate with the fact that the base loop space, that one truncated spaces are one affine, you get that n truncated spaces are n affine, simply because if you take the base loop space, you lower the degree of truncation. So if X is n affine, if X is n truncated, then the base loop space is n-1 truncated, then the double loop space is n-2 truncated, etc., etc., etc. And moreover, if our conjecture that the one affineness is actually equivalent to X being one truncated, then you can explicitly write the one before as follows. The Betti stack of X is n affine if and only if X is n truncated. So really the conjecture boils down to the one categorical level and not to the n categorical level. And finally, this is just, we have this functor also that concerns shapes of n categories over the coaffine stack of X and n categorical local systems. This is defined simply because the map is defined at the level of stacks, so you can pull back shapes of n categories, etc. And we expect it to be an equivalence of some suitable sub n+1 categories on both sides, just like it was in the case of shapes of one categories. The difficult part is really to understand what is the suitable sub n+1 category, but we are still working on it. But we expect this result to be true because, again, we know that if X is n+1 connected and it is sufficiently finite, then again, the cochains algebra over X and the chain algebra over the n+1 fold base loop space over X are Koszul dual, En+1 Koszul dual. So these should provide again a Koszul duality picture between modules, categorified modules over both sides. So I think I can conclude here. These are just some references for this talk, and thank you for your attention.
Yeah, thank you very much for the nice talk. I think we can give a round of applause. Are there any questions? And just unmute yourself and ask. Well, let me check. There's nothing in the chat.
Sorry, just a quick question from me. Martin.
Go ahead. Yes, Martin. Okay.
Now I just wanted to, maybe it's a silly question. What do you mean by a sufficiently nice topological space? Do you mean the connected ones, or?
No, I mean that, for example, if you take CW complexes, they are really spaces that are constructed in a combinatorial way, so attaching cells which are homeomorphic to closed disks in Rn for every n. So they have really good properties at the level of homotopy theory. Not every topological space behaves well with respect of the notion of homotopy, but those spaces that behave well, so for example, if you have an homotopy equivalence, you can, or better, a morphism that induces an isomorphism at the level of every homotopy group, in general, you cannot provide a honest map on the other side that provides the homotopy equivalence. But for those nice topological spaces, for example, CW complexes, you can do it. So if you have a map from X to Y, and that map induces an isomorphism on all homotopy groups, if both X and Y are CW complexes, then you really have another map of topological spaces that produces the quasi-inverse at the level of all homotopy groups. In general, you cannot do it. So many times in homotopy theory, you really stick to those nice spaces that have a good notion of homotopy and do not behave badly in that regard. So really CW complexes are just the spaces that you need.
Thank you.
I guess you could also use simplicial sets, for example, right? Or
Exactly.
Data. I had a question about, it was very interesting to see. I mean, you gave this example of Telemann at some point, right?
Yes.
One of coaffine. So if I now take the n categorical picture of this, so yeah.
Yes.
So if so what happens in higher dimensions? So do you get something interesting in this way? So you take like n-fold loops of G and relate to the classifying space and iterations of those?
Yeah, actually, I think Telemann, because both these results and the one that I'm talking about are spelled out without proofs, actually. They are spelled out as theorems, but there is no proof. So Telemann also tells that if you take G that is maybe n-connected, it could be something like that,
right,
or n-1 connected, then to make it act on a n category is equivalent to giving the datum of a En+1 algebra morphism between the chains over the iterated loop space over G and the En Koszul cohomology. The fact is that the En Koszul cohomology are better for now. It's not very well written in the literature. There is like the dreamful centers theory, etc., but there is no like a good picture that relates having a module structure on the modules over the base loop space and the Koszul cohomology that we have instead in the one categorical setting. But still, we expect it to be true, and actually, we are not willing to think too much about it for now, but we expect that by reading carefully the literature on n categories, you should really obtain this picture from the n categorical result, the n categorical monodromy equivalence that we provided later. So yeah, it should work like this, yes.
And if you let n go to infinity, do you have an infinity version in some sense out of this? In some as a limit?
Actually, we do not have it because for once, infinity connected spaces are just contractible points, the contractible spaces. So the theory is quite narrow. Moreover, there are two notions of infinity categories, which are not equivalent. So you should one should be careful to see which infinity category to consider. So we didn't deal with that actually. Also because the Koszul duality for E infinity algebras, while E and algebras are self-dual, infinite algebras are Koszul dual to Lie algebras, and that Koszul duality feature is quite known already. So we didn't deal with that.
And one last one. If you, I mean, you do this for topological spaces, can you generalize this to have maybe some side or some Grothendieck topology in slightly with good properties to have a more general framework of this also? I
don't know, because what we really use the fact that we are dealing with topological spaces in order to produce, for example, the Betti stack. Right. But this is something that we didn't investigate that much, but it could be like a possible route to pursue.
Okay, thank you. Do we have any more questions or comments? I think in the chat is not. If it's not the case, then let's thank Emanuele again for his nice talk.
Thank you. And
we will have the next one on the, was it 28th of April? No, 27th of April, right? I'm not completely sure. And we have Peter from Luxembourg, right? Is that correct?
24th.
24th?
Yeah.
Okay, 24th of April. Yeah, so thank you very much for joining us for today, and see you hopefully next time.